Hey everyone, thanks for coming to the talk and thanks for watching this video. I'm Binghui Peng from Columbia University, and today I'm going to talk about our EC 2021 paper titled Public Good Games in Directed Networks. This is a joint work with Christos Papadimitriou. I will start by defining public goods. A public good is a resource that benefits all regardless of who provides it. In economic theory, a resource or a good is usually classified by exclusivity and rivalry. In particular, a public good is non-excludable and non-rival. Here, non-rival means the availability or value of the good will not be affected if others use it. And non-excludable means once the good has been provided, one cannot stop anyone else from benefiting from it. There are a wide range of goods and objectives typically considered to be public goods. For example, infrastructure like street lighting, drainage system, clean environment like public parks, and clean air are considered to be public good. Also, the sanitation and immunity benefits are classified as public good, and scientific research is another example of public good. Finally, the results of this paper should be considered as a public good. Okay. Public goods are very well-studied economic topics. Then there's a much well-developed theory about it. There are many economic textbooks over the topic of public good. A central question in public goods theory is to characterize the strategic behavior of the agent. In general, each agent of the public good has the choice between producing the good and free riding. Due to the non-excludable property, everyone has the incentive to free ride. That is, everyone wants to enjoy the good without contributing it. So a key question is to characterize the strategic behavior and predict which player will choose to produce and which player will choose to free ride and benefit from others' contribution. Let's consider the following simple yet well-studied formulation. We assume there's just one type of public good, and the utility of the good is 1. We also assume the cost of the production is P, and we assume the price P is less than 1. To calculate the strategic behavior, we use the solution's concept of Nash equilibrium. That's to say, in an equilibrium, no one has the incentive to deviate from their current strategy. And for this example formulation, there's actually a trivial solution. That is, one of the players contributes and everybody else free rides. One can easily see this is a pure Nash equilibrium. There's one missing point from the previous formulation. The public goods game is meaningful only when one specifies interaction between players. That is, when can one benefit from what others produces. Most often, the benefit relationship is not universal. That's to say, the production of one player won't be beneficial to all the other players. And sometimes there's just some local benefits. And here, a network is a perfect model for this. We provide 2 motivating examples. First, suppose a public good is a CD or software license, which can be shared with other peoples. Of course, in real life, suppose some people owns a CD or software license, it won't share it to all the other peoples, but the license can only be shared among friends. Similarly, suppose the public goods are clean air, street light, or immunity extra. All these have a common feature, that is, it only provides local benefit. Formally, the public goods game is defined over a network, and the player only gets benefit from its neighbor in the graph. There's a bunch of literature on this, and previous work mostly focused on undirected graph. In this case, one can see pure Nash equilibrium always exists. Actually, they correspond to the maximal independent set of the underlying graph. And the research along this line mostly focuses on various aspects of equilibrium, such as the stability, the uniqueness, etc. But what about directed graphs? There are clear motivation for directed network. For example, social network can be directed, and any public goods game over such network is better captured by directed graph. Another example is the benefit in immunity and sanitation. These are also directional. For example, most epidemiology models are directed. Surprisingly, the directed networks are completely different from the undirected one, and there's a little literature on this. And the consensus in the literature seems to be that equilibrium is much harder to characterize when the network is directed. In contrast to undirected graph, pure Nash equilibrium may not always exist. For example, any odd directed cycle does not have pure Nash equilibrium. The focus of this paper is to understand the equilibrium of public goods in directed networks and the strategic behavior from the computation lens. We provide complexity and algorithmic results regarding the computation of equilibrium. In particular, we show it's NP hard to decide whether pure Nash equilibrium exists, and a mixed Nash equilibrium is always exists as guaranteed by Nash's theorem, but we show it's PBAD hard to find one. Finally, we show when the underlying graph have bounded trivials, then there's a polynomial time for finding an approximate Nash equilibrium. Finally, we also have some extensions. We provide similar result for the divisible version of the problem. The results are similar, but the techniques are different. And we also generalize the public goods game to more general monotone utility functions than the step function we discussed before, and we prove our complexity dichotomy result for the existence of pure Nash equilibrium. In this talk, I will focus on the following three results. I will first talk about the hardness for finding mixed Nash equilibrium, and then I will talk about the polynomial time algorithm for directed graph with bounded trivials. Finally, I will talk about the generalization and the dichotomy result for generalized public good games. Okay, I'll start from PBAD hardness of Nash equilibrium. And roughly speaking, our proof has two parts. We first introduce an intermediate game called threshold game, and then we prove a reduction to public good game from threshold game. Finally, we show the PBAD hardness of this threshold game. First, I will introduce the threshold game. A threshold game is defined on a directed graph G, and we use V to denote the vertex set and E to denote the edge set. And there's a real number xv associated on each node V. We can define equilibrium on the threshold game, and the equilibrium condition guarantees that for each node V, xv equal to 0 if the summation of its neighbor is greater than 1/2, and xv equal to 1 if the number on its neighbor sum less than 1/2. And finally, xv can be any number between 0 and 1 if the summation of its neighbor are exactly equal to 1/2. And we prove in our paper that the equilibrium of public good games and threshold game can be transformed to each other. We then prove the PBAD hardness of the threshold game through a reduction from the generalized circuit problem. The generalized circuit problem is introduced by Xi Chen and Xiaotie Deng in 2006, and the result has been strengthened by Aviad Rubinstein in 2018. Roughly speaking, the generalized circuit problem consists of a type of arithmetic and Boolean gadget, including the 1/2, the times 1/2, equal, plus, minus, less than, and, or not gate. And it's pretty hard even to find the absolute approximate solution to the problem. So surprisingly, we prove that the threshold operator defined on the threshold game is capable of simulating all these 8 types of logic and arithmetic gadget. Here's a sketch of the reduction. The key building block of the reduction is through the introduction of a new gadget named 1/2 minus. For this gadget, there are two inputs and one output. And the output satisfies the following expressions. That is, the output equal to the half minus the summation of input. The gadget can be constructed through a directed circle of shown in the red figure. I will omit the detailed computation there, but we know that the construction of arithmetic gadgets, including equal, plus, minus, and the logic gadget and or not, can be derived from the basic building block. The construction of 1/2 and times 1/2 are more complicated, and it is constructed through a delicate composition of this building block. Finally, we also proved PBAD hardness for finding epsilon approximate equilibrium of the public good games, and this extension requires some more extra work. Okay, then I will go to our second result, and I will present a polynomial time algorithm for bounded tree-based graph. The tree-based is a widely studied concept in graph theory, and intuitively speaking, it measures to which extent the graph looks like a tree. I will omit the detailed and technical definition of tree-based, but I just want to mention that many simple or complex graphs have low tree-based. For example, a tree and a path have tree-based 1, while a cycle has tree-based 2. Our major result is to prove that when the tree-based is suitably bounded, that is, the tree-based is less than log over log n, where n is the total number of vertices in the graph, then one can find an epsilon approximate equilibrium of threshold game as well as the public good game in polynomial time. And we remark we achieve an exponential improvement over the dependence of maximum degree over previous result for general graphical game. I will then give a very high-level overview on the key ingredient of our algorithm. Roughly speaking, it first discretizes the strategy space into small grids, and then we design dynamic programming on the discretized grids. In particular, we discretize the entire continuous strategy space into the discrete grid, and the size of grid delta equal to the mean of d over epsilon and the log over epsilon. We prove the existence of an epsilon approximate equilibrium over the grid via probabilistic method. In particular, we make use of the concentration of binomial variable. We then design a novel dynamic programming approach on this discretized space, and we show that one can find an epsilon approximate equilibrium in polynomial time. Okay, finally, I will talk about a generalized public good game and a dichotomy computation result on finding pure Nash equilibrium. Instead of the simple step utility function I discussed before, to be more concrete, step utility function means the player will be happy if someone in the neighbor contributes, and the player will be not happy if none of the neighbors produce the good and they will produce the good itself. We take the utility of always to be a same monotone and symmetric function over its neighbor. And the key question here is which monotone function are hard to find a pure Nash equilibrium and which are easy. We show a sharp dichotomy result on certifying whether pure Nash equilibrium exists, and we identify 3 tractable cases. First, we call the steep utility. In that case, the cost of production is so large that no one produces the good. And in this case, a pure Nash equilibrium exists as no one will produce the good. And there are another trivial cases which we call the flat utility. Here, the production is always more beneficial than free ride. So there's also a trivial equilibrium there. That is, all the players will choose to provide. Besides these 2 trivial cases, there's another checkable cases where the utility function is alternating between steep and flat. Here, the equilibrium can be computed via solving linear equation over finite field. Besides these 3 trackable cases, we prove that all other cases are NP-hard. Finally, I will wrap up the talk by mentioning a few future research directions. First, it will be interesting to characterize the equilibrium computation for public good game with general utility function. And in particular, is there any, say, PP80 hardness dichotomy result there? Second, for general utility function, pure Nash equilibrium may not always exist, even for undirected graph. So the research question is that, can one characterize the computation complexity there? For general utility function on undirected graph. both of the question is challenging, and it will be interesting if one can figure out the solution. Okay. Thanks again for watching this video and attend this talk. I will end the talk there.